for me to be able to speak here. And I just wish, as everyone, that Professor Zelevinsky could be here to celebrate with us. I was actually hoping to see him in this conference, to be able to grab it up, to grab this work up and post the first part of this work in the archive. So I hope to be able to post something in the archive soon. All right, so these mutations of species with potentials, somehow one of the aims is to try to extend Derksen-Weyman-Zelevinsky's mutation theory of quivers with potentials to the skew-symmetrizable case. So let me start by mentioning some related works. So well, I have to start from the inspirational side. Are the works of Labringel, that provide the non-simply laced version of Bernstein-Gelfand-Ponomarev reflection functors. And well, as I just said, the works of Derksen-Weyman and Zelevinsky on the mutation theory of quivers with potentials and applications to cluster algebras. Okay, and then, well, somehow like earlier approaches to earlier related approaches are, well, given by the work of Laurent de Monet, Grégoire Dupont, Bertrand Geffac, Dylan Ruppel, and David Spire, and Hugh Thomas. And when I say related approaches, what I mean is that they either attempt to provide a mutation theory of some sort of species with potentials, which would be the case of de Monet and Geffac, or an approach to some categorification of skew-symmetrizable cluster algebras via representations of valued quivers. Okay, if I have time at the end, I will say a few words on similarities and differences. But okay, just I mean between our approach and those approaches. But okay, this is if I have time. So let me start with the plan of the talk. So I'm going to start with weighted quivers, which is kind of just a different way of saying valued quivers. To our assumptions, unfortunately, we haven't been able to handle the most general situation of skew-symmetrizable matrices, only a class of them, which I will say which. Then path algebras, so it's the algebraic combinatorial setup for our potentials. Mutations. Unfoldings. Well, and again, if I have time, representations. Okay, so let me start with weighted quivers and the relation to skew-symmetrizable matrices. Okay, so let's start with just how we are going to skew-symmetrize our matrices. So a n by n integer matrix is skew-symmetrizable if there exist positive integers d1 to dn such that db is skew-symmetric where, well, D is the diagonal form, the diagonal matrix formed with these entries. So where okay, and then as an example, which will be our running example, it's this B. So 0, 1, 0, negative 1, negative 2, 0, 2, 0, 0, negative 1, 0, 1, 3, 0, negative 3, 0. And here, well, it's easy to see that the diagonal matrix can be chosen as 1, 2, 1, 3. Okay. So, well, given a skew-symmetrizable matrix and a fixed skew-symmetrizer, we can associate a weighted quiver. So, when I say weighted quiver, what I mean is a pair Q, comma D both, such that Q is just a regular, a usual quiver, just a finite quiver, and this is a tuple of integers attached to the vertices of the quiver, positive integers. So it's a tuple of positive integers to the vertices of Q. Okay, so it's it's just a quiver where we have assigned some weights to the vertices. Okay, and the way a skew-symmetrizable matrix B gives rise to such an object is as follows. So let B n by n skew-symmetrizable. Okay, and then define QD as follows. Well, first of all, the vertices of Q are going to be the integers 1 to n. So vertices 1 to n. Second, so for all ij vertices, if bij is greater or equal than 0, then we put these many arrows. I'm going to say how many in a second. From j to I. So I always go to the left. So from j to I. And the number of arrows is the GCD of di dj times bij divided by dj. All right, so I told you how many arrows. I mean, you can easily check that this is indeed an integer. All right, and well, what weights am I going to put in the vertices? Well, a skew-symmetrizer of D of B will give me that information. So skew-symmetrizable with skew-symmetrizer D. So we define well the tuple D is going to be given by diagonal entries of D. Okay, so it's fairly simple. So, so I guess here maybe so in this particular one, with this skew-symmetrizer, the associated quiver looks as follows. So vertices are 1, 2, 3, 4. Arrows go as in a cycle. And if you want to record the weights, it would be 1, 2, 1, 3. So this would be the tuple D, and this is Q for this matrix. Okay, so I'm sorry. I'll come back to that example later on. And then the easy lemma is that for D fixed, this assignment B goes to this QD as defined here is a bijection. So it's a bijection between the set of skew-symmetrizable matrices with this specific skew-symmetrizer and the set of all weighted quivers with this fixed weight tuple. And in particular, when B is skew-symmetric, this specializes to the well-known bijection between skew-symmetric matrices and two acyclic quivers. So maybe here I would have to say, well, with Q two acyclic. And by two acyclic, I mean that there are no oriented two cycles. All right, and then we know by the works of Fomin and Zelevinsky that there's a notion of mutation of skew-symmetrizable matrices. So we should have a corresponding notion for weighted quivers. So when one translates the notion of mutation of skew-symmetrizable matrices to weighted quivers, one obtains the following. So, so let me go back here. So, definition. Well, my input is QD and the vertex of Q. And then define the mutation mu k of QD in 3 steps. So in the first step, we introduce composite arrows. So it's every time we have an arrow incoming to K and an arrow outgoing from K in the quiver, we add not one composite arrow, but this many. GCD, DI, DJ. Times DK. GCD, DI, DK. GCD, DK, DJ. Composite arrows. So from J to I. Okay, that's the first step. And the second and the third step go as usual, as the usual quiver mutation, just as in the skew-symmetric case, namely reverse arrows incident to K and delete 2 cycles if there are any. So second step, reverse arrows incident to K. And third, remove 2 cycles, oriented 2 cycles, one by one. Okay, so in the example here, let's say that we want to mutate with respect to 4. Then in the first step, I have to add 3 arrows, because here the GCDs are just all 1. Okay, reverse arrows is incident to this vertex. Sorry, I said with respect to 3. No, it's with respect to 4. Okay, and here, well, there are no 2 cycles in the final in this quiver. So here, the third step is not even necessary. So this would be mu 4 of my original quiver Q D, and well, the tuple remains the same. Okay, so tuple D remains the same. And this is because when mutating skew-symmetrizable matrices, the same skew-symmetrizer works for B and for the mutation of B. So that's why we just keep the same tuple D. Okay, so that's the stuff on weighted quivers. So maybe here it's time for, yeah, I think. So this operation has the same property. So it's an involution. So mu k square of QD is isomorphic to QD. Okay. Now, let me speak about the assumptions under which we work. So this is. Okay, so the strongest assumption is actually that QD is what we call strongly primitive, which means that this tuple of positive integers consists of pairwise coprime integers. So GCD of DI dj is 1 for all I different from j. This is a rather strong assumption in some sense. I mean, it's obviously not all skew-symmetrizable matrices can be realized by skew-symmetrizers with this property. I mean, I would call the corresponding matrix B as well strongly primitive. Okay, so that's one assumption. Yeah, not that I know. Like even from surfaces with orbital points, it's not the case. Yeah. In a way, yeah. On the positive side, there are non-unfoldable matrices covered by this. So it's like on the positive side, we are able to cover some cluster algebras that cannot be unfolded. I will talk about that at the end. Yeah, but otherwise, yeah, the answer is no. I haven't seen. Yeah. Okay, and the next, the next.
These assumptions are needed for what is coming next, not
Right.
for what you just said.
No, yeah, no. Otherwise, this. Yeah, yeah. Okay, now the next assumption is on what will be our ground fields for the species. So let D be the least common multiple of the members of the tuple. So we are going to take F to be either a finite field of characteristic congruent with 1 modulo D, or a field of p-adic numbers where P is a prime, again, congruent with 1 modulo D. What this assumption guarantees is that there exist enough roots of unity inside F. Okay, and then, well, these are our two assumptions, and then we will, let's say, as a matter of notation, for EF is going to be either in either the unique degree D extension of F, or the unique degree D unramified extension of the p-adic numbers. All right. So what's the main thing? The main thing is that this is in either case, this is a cyclic Galois extension. Okay, and furthermore, we have this lemma, which is under these assumptions, there exists V in E such that the set, let me call it BE, consisting of the first D powers of D, is an eigenbasis of the extension. By eigenbasis, I mean a basis of E as vector space consisting of eigenvectors of all elements of the Galois group. All right, and moreover, if denoting Vi equal to V d over di, the set Bi equal to 1 Vi square, etc., Vi di minus 1, which is also the intersection of Be with Fi. And I didn't say what is Fi, sorry. Is eigenbasis. I will say what is Fi in a moment. But I guess you can guess it already, which is Fi is unique degree di sub-extension of E. All right, and moreover, I mean, here is there's there is an obvious property of this basis, which is when I multiply two elements of such a basis, I get an F multiple of another element of such a basis. So these are like almost closed on their multiplication. This basis, which we use heavily. Okay, so let me talk about path algebras. Okay, so far the input I have is a strongly primitive weighted quiver and a choice of a field extension that induces this other data. Yes. This is well denoting VI. Okay, this is equal to the intersection of BE with FI, and this intersection is an eigenbasis of FI over F. Yeah, either of the. I mean, yeah, whichever you want. Yes. Yeah, for applications to cluster algebras, at the end, I think we prefer this one. But I mean, whatever I'm going to say also works for this. Okay, path algebras, which is kind of well known. So this is mainly for notation. So I'm going to denote by R my ground semi-simple ring, and this is going to be the sum of the fields attached to the vertices. And A is going to be an RR bimodule, which is going to be Fj tensor over F, Fi. I know this is some sort of stupid way of writing the composite of the fields Fi, Fj, because the intersection of these two is F. But I like it this way because this gives me some nice way of dealing with the arrows of the quiver. So I prefer some sort of stupid notation. And this I'm going to call the vertex span of QD. Well, over the extension E over F, and this is going to be the arrow span of Q D over the extension. This is what Laban-Ringel called a modulation of the valued quiver, or also species. And any species, so what I'm calling arrow span is what is very commonly referred to as a species. And then every species gives rise to complete path algebra, which is L. I have to tell you what L is, and I'm going to do so in a second. Okay, so complete path algebra. And well, the usual path algebra. Okay, here AL denotes the L-fold tensor product of A with itself over R. All right, so we have at least some sort of, well, at least a definition of what a path algebra is, what complete path algebra is. But then, yeah, let's see. Can one find a nice basis of such a path algebra? In other words, can one find nice basis of AL? And in this case, is that given our assumptions, the answer is yes. And this is well, quite straightforward, which is that the set omega 0, A1, omega 1, etc., omega L minus 1, AL, omega L, where, well, these are arrows, so let's say AL, and then AL minus 1 finishes at the tail of AL, etc. Are just arrows, concatenable arrows. And the omegas live in the corresponding eigenbasis. So omega 0 lives in the eigenbasis of the field Fi attached to the head of Al. Omega 1 lives in the eigenbasis of the field attached to the head of Al minus 1, etc. And omega L lives in the field Fi or Fj attached to the tail of A1. So I'm just going to write it as the omega t's belong to the corresponding eigenbasis. Okay, so not all elements of the eigenbasis BE are allowed every time. It's just they have to live also in the corresponding field Fi. Okay. So we have now a nice basis for the set of, for a nice basis of paths. Let me call such things paths for this L-fold tensor product. So we call such a omega naught, A1, omega 1, AL minus 1, a path on QD. And, well, in principle, I should say over the extension E over F. I'm sorry? Yes. And I'm sorry, yes. Is a basis of AL as an F vector space. So yes, thanks. Okay, so this is going to be useful when I define what a mutation of a species with potential is. So let me first tell you what some things about potentials. So definition, as you may expect, is that a potential is a possibly infinite linear combination of cyclic paths with this notion of path. So a potential on my arrow span A Okay, and now we use this nice basis to give an explicit definition of what the partial derivatives, the cyclic derivatives should look like. So, well, what we do is we define it on cycles and then extend it to the space of all potentials. So, given an arrow of the quiver and a cycle and a cyclic path, omega 0, A1, etc., we define the cyclic derivative of this cycle to be, and we pretty much follow the same rule as Derksen-Weyman-Zelevinsky, which is the sum from k equal to 1 to L of Kronecker delta of A with the kth arrow, and then omega k, ak plus 1, al, omega L, omega naught, A1, omega k minus 1, omega a k minus 1, omega k minus 1. So, cyclic derivative. Okay. And then, as I said, one extends the notion of cyclic derivative to the space of all potentials by linearity and continuity. So now, given a potential, one can define a Jacobian algebra. So one defines, given a potential S on A, well, define the Jacobian algebra to be the complete path algebra modulo the closure, the topological closure of the two-sided ideal generated by the cyclic derivatives of S. Okay, and then, well, some more definitions. So, let me call a pair AS species with potentials. If it's, I mean, I'm given a potential on my arrow span A, I call AS species with potentials, a species with potential, and an SP, so a species with potential. So this is a shorthand for species with potential. AS is, so one such pair is reduced if it does not involve two cycles at all. So if in S, if no oriented two cycle or cyclic path of length 2 appears in S at all, and trivial if it's kind of in the opposite end. So if S2 is actually equal to S, which means in S, S consists only of two cycles. And moreover, when one takes the cyclic derivatives of S, one spans the whole arrow span as R by module. which to say, I mean, which makes sense because when taking cyclic derivative of a 2-cycle, one obtains a linear combination of arrows. Well, of paths of length 1. So in this case, it makes sense to ask whether one can span A itself. All right, and then one has the following analog of a result of Derksen-Weyman-Zelevinsky, which is given any AS with the only assumption that the quiver of which this one is the arrow span does not have loops. Is right equivalent to a direct sum. Well, to a direct sum where this is trivial. This is reduced, and this is a trivial SP. And okay, what it means is the following. So if I am given one such speciation with potentials, well, I'm only assuming that that A doesn't have loops, but it may have 2 cycles. And the thing is, S has a degree 2 component, a degree 2 part, that involves only cyclic paths of length 2. And the problem is that some of the arrows that occur in these paths of length 2 may also be involved in the higher degree terms. And what one does is what this theorem is saying is that up to applying an automorphism of the complete path algebra, one can separate the degree 2 part and the terms of higher degree. One can completely separate them. And well, the thing is, if one now takes the Jacobian algebra of such a thing, all this part is killed in the Jacobian ideal. So one can recover the Jacobian algebra of AS using this part, which involves only paths of length at least 3. Okay, and then the remark is that just as in the case of quivers, this arrow span may have 2 cycles. S doesn't involve any cycles of length 2, but A may have. So remark, A red may have 2 cycles. Oh, sorry, and I'm again writing here. Which, from the cluster algebra point of view, is somehow undesirable. And it's a source of a lot of difficulties. And another remark is that our proof of this, I mean, for this theorem, one can pretty much apply the proof of Derksen-Weyman-Zelevinsky word by word. I mean, so this is one can just kind of look at their proof and see that it just copies in this situation. Okay, so let me talk about mutations, and here is where things begin to be a little bit different from Derksen-Weyman-Zelevinsky, at least in the proofs of the statements. Okay, so mutations of SPs. So the input of such a mutation is going to be a 2-acyclic SP, AS. Remember that I'm working under certain assumptions, so this is not the full general case. Okay, and also a vertex of the quiver, and the output is going to be a reduced SP, mu k AS, and well, hopefully 2 acyclic. So here, when I say 2 acyclic, I'm referring to A being 2 acyclic. Okay, so I'm sorry? Well, it won't be 2 acyclic always. Yeah, I'm going to talk about that. Yeah, I'm going to say yes. Yeah, but if you just take any potential, it may be sometimes 2 acyclic, sometimes not. Okay, so remember that the mutation of weighted quivers was defined in 3 steps, right? So let me denote by mu k of A the arrow span of the weighted quiver obtained from QD after applying only the 2 first steps, so before removing 2 cycles. Well, here is of mutation of weighted quivers. So of weighted quivers. Okay, and in this arrow span, we define the following potential. So mu k tilde of S, of my given S, I'm going to it's going to be again bracket plus sum over all arrows incoming and outgoing, BA, of the sum of omega running in the eigenbasis in the eigenbasis of the field Fk, of omega inverse B star B omega A star. All right, and here, I have to hurry up. So here I have to tell you a bit about this bracket. So, okay, the thing is, every time I have BA, if you look, okay, every time I have this, so every time I have an incoming and outgoing arrow from in the quiver Q, well, if you look at the mutation rule that I told you at the beginning, I have to add exactly DK composite arrows, and what I do is this eigenbasis has exactly DK elements. So the DK arrows, sorry, the composite arrows, now I can label them by the elements of BK. So, and they are BA, B, VKA, etc. B, VK to the DK minus 1A. So now I just label them that way. Okay, so this is this bracket here. Well, this B and A are the arrows going in the opposite direction that I do in the second step. Okay, and this bracket of S comes from the following isomorphism of bimodules. So if I have fj tensor f fk tensor over fk so this is isomorphic to the direct sum, and again this is dk copies of fj tensor over f fi. And so what I do is here an element of the form x tensor 1 tensor I don't know, omega if you want, tensor y. I send it to x tensor y in the copy corresponding to omega, and that would be my bracket of this guy. And well, then I just remember that that when I put this tensor product, I'm really putting an arrow, so that these two tensors really represent multiples of arrows. And in that way, this I can also think of these composite arrows as living in the corresponding copy of the corresponding direct summand. All right, but the problem is that this guy may have two cycles. So I define mu k of as to be read of the tildes. So reduced part of mu k tilde a comma mu k tilde s. Okay, and then just the warning is that precisely because a red may have two cycles, well, my mutation here, this reduced part may have two cycles. So the potential doesn't involve any two cycles, but the arrow span, the arrow span may involve two cycles, and that is a problem. All right. Now, Derksen-Weyman-Zelevinsky managed to prove that given any two acyclic quiver, one can always find a potential such that the result of such mutation is two acyclic, and not only after applying one mutation, but after applying any possible sequence of mutations. Unfortunately, we don't have such a strong result. We have something slightly weaker. But so, okay. So let me tell you what we can prove. So this is theorem. So let QD be a weighted quiver. Okay, and K1 up to KL, any finite sequence of vertices of Q. All right, then we can prove that there exists a field extension K of F, linearly disjoint from E over F. Okay, I'm not going to write that. Such that, and I'm probably running out of space. such that the arrow span of QD over admits a potential S with the property that mu K1 of AS, mu K2, mu K2, mu K1 of AS, etc., mu KL, mu K1 of AS. All of them are 2 acyclic. So if I fix the sequence of mutations I want to perform, then I can find some arrow span and some sort of locally non-degenerate potential on it. Okay, and if my field F is actually the p-adic field, then I can take this K to be equal to F, to the p-adic field, to the ground field. And moreover, I can actually take, there actually exists some potential that is globally non-degenerate. So in the case where the underlying field is p-adic, we can prove the analog of what Derksen-Weyman-Zelevinsky proved. So if F is QP, we can prove existence of non-degenerate potentials. Which means potentials such that the fact that the mutations are 2 acyclic does not depend on the fixed sequence. Okay.
Instead of taking a sequence, you just take like a ball inside the exchange graph. Like any sequence of L mutations.
Right, can also do it.
You can also do it.
Yes.
So it's not like when you go here, it's one condition, and you go there, it's
No.
potential, and you cannot satisfy both.
No, we can do it in the ball. Yeah.
Okay. Let me put a quantifier.
I'm sorry.
You can put a quantifier to make this stronger. For any L, there exists a
Okay.
for any sequence.
Right. Yes. Yes. So can I have a couple of minutes more? Or, All right. So I just want to say a few words about unfoldings. So the matrix that I showed you at the beginning is actually not unfoldable from the cluster algebra point of view, and this was shown in unpublished work by David Spire and Zelevinsky. Well, okay. So this matrix. Okay, it would take me a long time to actually write down all of this, but so let me just say the matrix B equal to the first one, 0, 1, 0, negative 1, minus A, 0, 0, negative 1, 0, 1, B, 0, minus B, 0. Sorry, and here I meant is not unfoldable. Right, and this was Spire. Right. Yeah, and it's a bigger matrix. The one. Yeah. Yeah, and I don't know if I mean I don't know what your proof was, but I mean you can actually replace this by any B and any A, where well. Yeah.
I was under the impression that Andrei was under the impression that any skew-symmetrizable matrix is unfoldable. It's unfoldable. Right. So while I was in Boston, he asked me, he said, David, you should really prove this. And also, that was the conversation that led to this example.
Yeah, just let me say a couple of words. So what I mean by not unfoldable from cluster perspective is, okay, if I just look at this matrix by itself, just by itself, and I don't care about cluster algebras, I can unfold it. That is, certainly is a skew-symmetric matrix that sort of covers it. Or if you want, there is just a quiver that covers the corresponding weighted quiver. Now the problem is that I would like that the mutation of this matrix also has an unfolding, and that moreover that the mutation of the unfolding actually goes to an unfolding. That's what is not satisfied here. If you give any unfolding, the sequence of mutations it would be 2, 3. Sorry. It would be 2, 4. So mu 4, mu 2. That's already of this matrix is already incompatible with unfolding. Okay, and just finally, this does not satisfy the criterion of that de Monet gives in his paper. Okay, and I ran out of time, so thank you.
Any questions? Maybe the assumption of the distributed dynamically is one
it enters in how you define the cyclic derivative. But also when, okay, I didn't talk about mutations of representations, but in order to be able to define mutations of representations, we use that assumption very strongly. Yeah.
But in non-creative theory, a potential is a scalar function on the space of representations of the quiver, and the representation of Jacobian algebra are crystal points. Is it the same here with various field extensions?
Okay, not this I don't really know. I'm sorry. No, yeah, I don't know.
All right. Anything else? Thank you again.